Hi everyone, today we're going to cover polyprotic acids. What is polyprotic acid? It is an acid that has more than one ionizable hydrogen atom. They will ionize in successive steps, each one with its own Ka value. For example, if we take sulfuric acid, it will ionize in the first step to give the first hydrogen ion and forming hydrogen sulfide ion minus 1 charge. Ka1 is 1.6 times 10 to the minus 2. Now then in the second step, this hydrogen sulfide ion will ionize to form the second proton and then forming sulfide 2 minus ion. Ka2 is 6.4 times 10 to the negative 8. Now you would notice that the Ka1 is much greater than Ka2, meaning the sulfuric acid is actually a stronger acid than the HSO3 minus ion. This is because the first proton will separate from a neutral molecule, while the second proton separates from an anion. And the anion being negative will hold onto the proton, which is positive, more tightly, making the proton more difficult to remove. Let's try practice problem number 1. Write the successive ionization steps of phosphoric acid H3PO4. Now there are 3 hydrogen ions in here, so the first step is to remove the first hydrogen ion, forming H2PO4 minus ion, Ka1 7.5 times 10 to the minus 3. Make sure that you account for all the charges of the ions. Now we take the H2PO4 minus ion and take away the second proton, forming HPO4 2 minus ion, Ka2 6.2 times 10 to the minus 8. And the third step is to take the hydrogen HPO4 2 minus ion to donate the third proton, forming phosphate 3 minus ion. And K3 is 4.8 times 10 to the negative 13. And again, you see the successive K values are decreasing. Practice problem number 2. Find the pH and the carbonate ion concentration of a 0.1 molar diprotic acid, H2CO3 carbonic acid. So the first step, we take carbonic acid and ionize to form the first proton and hydrogen carbonate ion. K1 is 4.3 times 10 to the minus 7 from the book. Now then we set up the equilibrium molarity of the species, the carbonic acid being 0.1 minus X, X being the change, and the hydrogen ion and hydrogen carbonate ion, each having X being the molarity. Now we set up K1, which is the concentration of product over reactant, and assuming that X is very small compared to the 0.1 molar, because the Ka1 value is so small, the change has to be quite small. So we can drop the X and solve, and X, which is hydrogen ion concentration, is 2.1 times 10 to the minus 4 molar. Continuing. Now in the second ionization, we take the hydrogen carbonate ion and form the second proton with the carbonate ion formed. Now, this is important to note that we start out with 2.1 times 10 to the negative 4 molar for the hydrogen carbonate ion and the hydrogen ion, because that's a carry down from the first step. Both of these ions are in the beaker while the second dissociation is happening. Now let Y be the change, so we take away Y from HCO3 minus ion, but we add Y to the hydrogen ion and the carbonate ion. Now setting up Ka2, 5.6 times 10 negative 11, equal to product concentration over reactant concentration. Now I purposely put the Y in blue, meaning that is so small and insignificant, which can be dropped while solving the problem. Now Y now is solved as 5.6 times 10 to the minus 11 molar. So we notice that the carbonate ion concentration is actually equal to Ka2. Therefore, the conclusion is that whenever you have a diprotic acid and you want to find the anion concentration, it should be equal to Ka2. Now the hydrogen ion concentration is equal to that of the first proton plus the second proton. However, the second proton concentration is so small compared to the first one, we can drop it and ignore it, and use the pH of 3.68 which is basically determined by the hydrogen ion from the first dissociation. The formation of the hydrogen ion in the first step inhibits the formation of additional hydrogen ion in the second step by Le Chatelier's principle. To sum up what we have learned today, we have learned how to write the dissociation of polyprotic weak acids in successive steps. 2. We explain how successive Ka values of a polyprotic weak acid are increasingly smaller. And lastly, we determine the pH of a polyprotic weak acid such as carbonic acid. I hope that you find this video helpful to you. From the team of MLCA, we'd like to thank you for watching the video, and we look forward to seeing you again soon.